Pure substance. Matter is classified into two: pure substance and mixture. What's pure substance? Pure substances are the substances that are made up of only one kind of particle and have a fixed or constant structure. What about the mixture? Mixture is a physical blend of two or more substances that preserve their identities and are not chemically linked. The pure substance is further divided into elements and compound. We learned about elements and compound in our previous lessons, yes? Elements and the mixture is further divided into a homogeneous mixture and heterogeneous mixture. What does an element mean? An element is made up of only one pure substance. It cannot be separated into simpler substance by physical or chemical means. Compound is composed of two or more elements that are chemically combined. What's a homogeneous mixture? Homogeneous mixture is a mixture in which the composition is uniform throughout the mixture. For example, you could say mixing in two paints or mixing in milk and with water. If you mix them, they're going to have a composition which is going to be uniform throughout the mixture, yes? So what's a heterogeneous mixture? A mixture in which the composition is not uniform throughout the mixture. An example would be a cereal in a milk wherein the composition is not uniform because there's the cereal that's solid in state and milk that's liquid in state. Yes, that's an example of a heterogeneous mixture. We'll see more examples in the next slide. An example for element would be oxygen, hydrogen, nitrogen. Compound examples would be water, that's H2O. Can you see here that there are two different elements, H2 and O, two different elements combined together to form a compound according to the definition, yes? And there's also carbon dioxide and salt, NaCl. Examples of mixture, homogeneous mixture, examples would be Kool-Aid, air, paint, honey, lemon juice. Examples of heterogeneous mixtures would be trail mix, water and oil. Yes, they don't mix together. Yes, water and oil, the composition is going to be different. Yes, and then spaghetti sauce and also cereal and milk. Moving on to the next slide. Another example of a homogeneous mixture is salt plus water. Because the salt, though it's in a solid state, it gets dissolved. Yes, all solutions are mixtures, but because the solutions are evenly mixed, one substance dissolves in the other. That's why it's a homogeneous mixture. But when you put marbles and water together, they would be a heterogeneous mixture because the composition is different. There's a solid and a liquid, so that makes it a heterogeneous mixture. Moving on to the next slide. So what is a solution? Solution is where you dissolve solute in a solvent. Solute would be the salt or the sugar, and the solvent can be the water or milk, everything that's in a liquid state. So what's a solvent? The one that's in a liquid state. And what's a solute? It's in a solid state. So here you see there's solvent, the blue, for example, in here let's take it as water, and solute, that's the NaCl, that's the salt. So when you stir it, that's when it will make it a solution. How will you separate solution? How will you separate the solute and the solvent once they are formed solution? For that, you'll have to use the evaporation method. Evaporation is employed when you want to separate solid solutes from liquid solvent. The solute is evaporated away in the air. Here you can see there's a burner. There's a solution of water and salt, and when you burn it, all the water is going to get evaporated, and what will remain is the salt. So the next, properties of matter. There are two properties of matter: physical and chemical property. By the word physical, it describes how it feels, yes, how it looks, how it feels. Texture, hardness, luster, odor, sound, all of these are physical properties of any matter. What's a texture? Texture is the feel, yes. Hardness is how hard or soft it is. Luster is the shine of an object. Odor is the smell, and sound. And how do you measure the physical property of matter? It can be measured using density, melting point, and freezing point. What is a chemical property? A chemical property is when there is a chemical reaction. For example, like flammable or non-flammable, flash point, all those are chemical reactions. Example of some matter that can cause a chemical reaction is water, because water can dissolve and water can rust metals, and it can also react when in contact with a solid. Yes. An example would be you take a flour and then you put water in it. When you mix, it creates this dough. That is a chemical reaction. Another example that can cause chemical reaction is acids. It can cause corrosion, yes? Corrosion on metals. Let's see more examples of chemical and physical reactions so you can understand better. A chemical reaction forms new product. For example, combustion. After the process is finished, all you'll see is ash. It will not be the same. Yes, you will not have the wood. It will be in the state of ash, rotting. The fruit cannot go back to its original form. Yes, rusting, digestion, all are examples of chemical reaction. Examples of physical reaction. Matter changes form, but not change chemical. It changes form, but its chemical identity remains the same. For example, melting. It can melt, but it's still water. It's still got that H2O molecules in it. You can boil, and the water might change into vapor, but there's still this H2O molecule in the water and the vapor. You can chop the wood, but the composition of the wood will remain the same. Same goes to the shredding of paper. You can shred the paper, but the composition of the paper is the same. Next, other examples of chemical reaction are photosynthesis, fermentation, washing, and baking. Now let's move on to another topic that's related, thermodynamics. There are 3 laws in thermodynamics that we are supposed to memorize it. The first law of thermodynamics is also known as the law of conservation of mass and energy. The second law of thermodynamics is maintaining equilibrium. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. You can pause and write this down on your notes so that you can memorize it for later. So now let's start with the first law of thermodynamics. I'm going to explain so that it's easier for you guys to memorize. The first law of thermodynamics states that energy can neither be created nor be destroyed. It deals with the amount of energy in the universe, and in particular, it states that this total amount does not ever change. It can only change form or be transformed from one object to another. So we'll see how that happens in pictures. So here you have 3 systems, yes? Open system, closed system, and an isolated system. So the heat transfer is different in each of these systems. In an open system, there is transfer of both heat and matter. In a closed system, there is transfer of just heat. In an isolated system, there is no transfer of heat or the matter. An example would be boiling a water in a pan. If you boil water in a pan, there is transfer of heat and also transfer of matter. How is the matter getting transferred? In the form of water vapor. Yes? So next let's move on to the closed system. You're heating the same pot, but this time you've got a lid on top of it. What happens? Just the heat gets transferred, whereas the matter remains inside. How do you know that? If you open the lid, you'll see that there are small droplets inside the lid. Yes? And that's how the matter stays inside. An example of an isolated system would be a flask. It has got an insulation inside it. So if you keep it closed, the heat is going to remain inside and also the matter is going to remain inside. So that's why a flask can have the coffee or tea or your water hot for a long time because the heat is not getting transferred outside. Another example of an open system. We know, as we have read in the previous slide, that the first law states mass can neither be created nor be destroyed. Here we see an example of an open system wherein you use the log and you burn it. In the end, you have ash and smoke. So what we must understand here is, at the beginning of the reaction, there was this 30 kg of log and 1 kg of fire. In the end, we have ash and smoke. That's the same, yes? It's 31, and this also adds up to 31. So that is what the thermodynamics first law states. The start and the end of the reaction, the matter is going to be the same. Next, the second law of thermodynamics. The second law of thermodynamics is maintaining equilibrium. Second law is maintaining equilibrium of variables like pressure, volume, and temperature. So let's go one by one. Volume. So if you place a cup of water at a higher level and it's connected to another cup at a lower level, what's going to happen? Water is always going to flow from a higher level to a lower level. So that's maintaining equilibrium. Another example is using temperature. So if you have 2 systems, or to make it easier, 2 rooms, okay, and they are connected in between. This room is warm and the other room is cold. If they are connected, what would happen is the particles from this room are going to go inside this and from this room they're going to go in this, and eventually you'll have the same temperature in both the rooms. So what's it doing in here? What's happening in here? There is maintenance of equilibrium in the temperature. Yes, previously we saw equilibrium of volume. Now we saw equilibrium of temperature. Next we are going to see equilibrium in pressure. Example would be the wind. So when the sun heats up the water, there is evaporation, yes, and there is condensation on the sky. So what makes the cloud move to the land area? That's because the pressure is high in the sea area. So the winds are going to naturally push these clouds to the land area. So that's how the pressure is maintained in an equilibrium. So the third law of thermodynamics, it's simple. It basically states that the entropy of the system approaches a constant value as the temperature approaches an absolute zero. I know it sounds confusing, but it's actually easy if you understand it. What they are saying is the particles are in motion when there is high temperature. As the temperature decreases, they're going to come in a constant value. They're not going to move anymore. They are more arranged because the kinetic energy, that is the movement of the particles, have got decreased.